So our next guest lecture today is by Luke Keltner, whom many of you, for many of you, he doesn't need any introduction because he's also involved as a lab instructor for this course. But briefly, Luke is a final year graduate student in our department, and he works on, do you have a title for your thesis yet? Or?
UV properties of Galileans.
UV properties of Galileans, that's what he works on, and you can ask him what that means afterwards. In fact, I should probably ask him what that means as well. But Luke, I was hoping, I wasn't sure what to hope for. I was hoping that he would either do a PowerPoint because he's a real master of animation, or I was hoping he'd do a chalk talk because he's also a master of cartooning. And apparently what he's decided to give us is a chalk talk, so that's wonderful. And so I'm going to hand over to you now, Luke. And this also continues the theme of doing talks on relativity today, which is nice because that's something we didn't get a chance to do in this course.
Oh, I've never used one of these.
Yeah, so you just put it in your pocket and,
Hello?
Yeah.
Where does this go?
Oh, you have to flip it onto something. You probably just get in your color. Yeah. Yeah, not your color, but fast. Yeah.
Is this going to be too loud? Oh.
Yeah.
Sorry, give me a minute. God.
Is that good? That's good.
Can you hear me? Okay. I have to be like Hermione and put this in. What?
You need both. I can clean that one up.
I probably won't need both.
Okay, I'll just send this one up and then you have the lower board. Okay.
Oh, the green means on. Okay. Let's see if I don't break it, if I put it on my belt. Okay, hi. My name's Luke, as Professor Mathur introduced me as. I think it's really cool what he does, which is, I'm sure you guys know, I just recently learned this, that he gets graduate students and professors to come and give little short talks about who they are, what they're into and stuff, and I think it gives you guys a nice, cool, unique perspective on why certain people are in physics at all. So what I decided to talk about is why I'm here in the first place at all. So why am I, at Case, a graduate student studying theoretical physics? And I guess the best way to do this, we have colors. Okay, so let's draw, so this is going to represent today. So this is April 24th, 2015. I don't know where that came from. So that's today. So here we go. For the past 5 years, I have been studying physics, theoretical physics, at Case as a graduate student. And some of you know me through TAing labs. 4 years before that, I was studying physics in undergrad at Miami University, the one in Ohio, not Florida, unfortunately. And then just for completion, I had 2 years of physics in high school, a regular class and an AP class. So in a sense, that's 5 plus 4 plus 11 years of being succumbed to physics, to learning physics. And that's a good portion of my life. That's like 40-something% or so. I don't know. I didn't do the math for that. So this is a long time. And you might reasonably assume that this has always been the case, that my interest in physics has gone back until I was born. But it turns out that's not the case. Before this point, not only did I not have an interest in physics, I thought it was stupid. I thought it was pretty dumb, and I didn't have any care for it. So what happened? there was a milestone in my life. And that milestone occurred maybe here, let's say. It happened at the movie theater, and it happened on November 22nd, in 1995, which I'm sure we all know is the day Toy Story came out. I went to the movies, I saw Toy Story, the movie ended, the lights came on, the credits started rolling. I was sitting in my chair listening to Randy Newman thinking, oh my God, this was the coolest thing I have seen and will ever see in my entire life. There's these guys in basement somewhere on computers just creating characters on the computer and animating them, and there's textures and lightings and shadows, and there's this cool story, there's talking toys. It's the coolest thing I've ever seen in my life. And so for this amount of time in my life, I knew that I was going to be a Pixar computer animator. And I don't just mean animator. I don't just mean that, I thought it would be cool if I ended up being this. I was taking classes in computer animation and graphic design. This is definitely, for sure, locked in stone what I wanted to do. And it was great. I loved studying it. I found it fascinating. I still do. I still go to see these movies just to see the movie. I don't care what's going on in the movie. I just want to watch it. So this is who I was for a long time. And before this, there was another milestone in my life. And this milestone happened at the movie theater. It happened on June 15th, 1994, which we all know is the day The Lion King came out. I saw this movie. I went with my neighbor. We went to the movie. We saw the movie. The movie ended, the lights came on, the credits start rolling. I was listening to Elton John thinking, oh my God, this is the coolest thing I have and will ever have seen in my entire life. There's guys in a basement somewhere drawing lions, and they flip the pages, and now the lions are moving, and they color the lions, they have backdrops, they have this awesome story. Jonathan Taylor Thomas is there. This is great. So I knew that I was going to be a Disney cartoonist. Cartoonist? Is that an I? It was not English that I was interested in. So I for sure was going to do this. I was taking classes in art at the community college. I knew for certain this is what I was going to do. And up to as long as I can remember, I always had an interest in drawing and art in general. To the point where my dad took me to UC, University of Cincinnati, to go to visit their art school to see if that's something I wanted to do with my life. I think he took me to UC though because he has a clinical obsession with Skyline Chili, but that's a whole other thing. But I was very, very serious about art and stuff. So you can see a natural progression from here to here, and then from here to here. But then, what the hell happened here? This doesn't make any sense. Why have I now spent 11 years of my life studying theoretical physics? What monstrosity of an event occurred right here to change everything I'm doing? Well, actually, before I tell you what happened, right before this wall occurred, I was in high school physics, and I hated it. My teacher would, you draw a triangle and go, oh, hey, look, there's a triangle, and look, oh, there's an angle now, and oh, now there's a square on the triangle, and uh-oh, the square is falling down. What's this? What's the acceleration of the square? And I think I was polite in the sense that I was just sitting in class, just not saying anything, just kind of waiting for the class to be over. But in my mind, I was like digging my eyeballs out of sheer boredom. And I don't mean boredom in the sense like, oh, this is a very easy problem. I can do this very trivially. Like, oh, I'm a master in physics. No, it was hard for me. It didn't come naturally to me. I had to work at it. But I found it boring because it was just so boring. You can't get me to care about that. I don't care. So during high school physics, I was like, oh, I can't wait to be done with this and be a Pixar computer animator. I cannot wait for that. But then, one day, I learned about something. And this line, the width of this line, represents about 10 minutes of my life. By the end of these 10 minutes, at the end of me learning about this thing, all of this shattered into pieces. I still loved it. I still love it now. But it got pushed aside to studying physics after I learned this thing, this one thing. I found it so fascinating. This thing taught me that nature, reality, the universe is much more interesting than intuition gives it credit for. It's a fascinating thing, and some of you might have already seen it. You've already been exposed to it if you've seen Interstellar, the movie. But it's called time dilation. And it's a consequence of special relativity, that thing Einstein discovered. I don't like how this is. There we go. Okay. That is working now. Okay. So time dilation deals with time. It exposes a subtlety about time. And what I mean by time is if we all had a watch on right now and we were instructed to snap, every second we'd all be snapping together because when a second passes, a second passes. That makes sense, right? We all just snap. But to understand the subtlety of this, we have to quantify that just a little bit. So I'm just going to do an itsy-bitsy amount of math with a very weird scenario, okay? So imagine that there's a spaceship. There it is, okay? At the top of this spaceship is a trampoline, and at the bottom of this spaceship there's another trampoline. Okay, so this is already kind of weird. Stick with me. Now there's a baseball here at the top of the trampoline. And this baseball is set in motion such that it just goes boop, 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 boop. It just goes up and down indefinitely forever in this spaceship. Okay? So we're going to count that as a second, as a snap. Every time the baseball touches the trampoline, it's a snap. It's a second. So snap, 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 snap. Okay? This is going to be our clock. It's just as good of a clock as any other clock. It's probably more expensive than the new iPhone watch, but it's a clock nonetheless. Now let's pretend we have Bob in this spaceship as well. And we just want to ask Bob, how much time does it take for this ball to go from the top trampoline to the bottom trampoline? So what we need to know for that is the distance, the height of the spaceship, and we need to know the velocity of the ball. So the height we'll call y, the velocity we'll just call vb, the velocity of the ball. So the time that Bob sees for the ball to go from the top trampoline to the bottom trampoline is just y divided vb, divided by vb. That makes sense. That's easy enough. It's just the distance the ball traveled divided by how fast the ball is traveling. But now, there's actually a second person. There's Alice watching Bob, thinking, what the hell is he doing in this weird spaceship? She's in a spacesuit, of course, because she isn't out of space and she doesn't want to die. But she watches this. So to her, this spaceship is actually moving. Okay? So, here's Bob still in the spaceship. So we ask the same question to Alice. Alice, how long does it take this ball to go from the top trampoline to the bottom trampoline? So she sees the ball actually go a different distance. Because this ship has some velocity itself. So the distance that she sees is the square root of y squared plus x squared, where x is just this distance. Okay? And the velocity she sees is also different. It's the velocity of the ship squared plus the velocity of the ball squared. Just the resultant vector business. And I can replace these distances I can replace x with the velocity of the ship squared times the time it takes Alice to see the ball, and I can replace y squared with that equation, so vb squared t Bob squared divided by vs squared plus vb squared. And what you end up getting if you solve for TA is that TA equals TB. What does that mean? That means that the amount of time it took the ball to hit the bottom trampoline for Bob is the exact same as the amount of time that it took Alice to see the ball go from the top trampoline to the bottom trampoline. That makes sense, right? We're all snapping together. So that should not be interesting. Don't find that interesting. That's okay if you don't. The interesting part comes along when Einstein was born. He looks at this and goes, "Nuh-uh, that's not right." Einstein said that the speed of light is the same for all reference frames. It's actually the same for all inertial reference frames, but I don't know how to spell the word inertial, so I'm not going to put that on the board. Okay? So first, you might say, well, why does this sentence have anything to do with what I just described? Okay, I didn't bring it. Okay, so we're now going to think of an almost exact same situation, except instead of trampolines, we're going to have mirrors, and instead of a baseball, we're going to have a photon, a little particle of light that goes the speed of light. Okay, this is going to be our new clock. And for Bob, you can go and do the math, and you'll get y. The time that Bob sees the photon, go from the top mirror to the bottom mirror, is y divided by c. And for Alice, since she sees this longer distance, she sees the square root of c squared tb squared plus the velocity of the ship squared ta squared, almost very similar to the last expression, except for this right here. She does not see a different speed for the photon, but the photon has traveled a larger distance. Because the speed of light has to be the same in all reference frames. To Bob, the photon just went down, and it went down at the speed of light. To Alice, the photon went this whole distance, but it also must have traveled at the speed of light. A consequence of that, if you solve for TA here, is that TA doesn't equal TB anymore. It equals TB divided by this thing. What this means, if this ship, the faster this ship is traveling, literally the slower Bob will age relative to Alice. What I mean by that is if the ship is going 95% the speed of light, TA equals 3.21 TB. What that means is every second Bob experiences, Alice experiences 3.2 seconds. For every year Bob experiences, Alice experiences 3.2 years. It is truly the case that Alice and Bob no longer experience time the same. It gets as weird as something called the twin paradox, where if Alice and Bob are twins on Earth, so here's Bob, here's Alice. Let's say they're both 20 years old. One more year till they can start drinking. Alice gets sick of Bob, so she gets in a spaceship and travels to a planet that's 10 light years away. And a light year, of course, is how long it takes light to get there. So let's say she travels at 95% the speed of light again. And then she realizes she misses Bob and comes back. Bob will have aged 20 years in this trip, assuming that it takes just a little over 10 years for Alice to do this, because she's going almost the speed of light. So for Bob, Alice goes 10 years 10 years, Bob is now 40 years old. He's probably married with a few kids, thinking about getting a divorce. Who knows? Alice will come back, see 40-year-old Bob, and she will be 26 years old. She will have literally aged a different amount than Bob. This is something your intuition does not let you see. This is something that you only see when the speed of light is either very small or you're going very close to the speed of light. For instance, if you're in a car going 65 miles per hour, a person having a picnic outside watching you drive your car will age, for every 1 second you experience, they will experience 1.0000000000000000005 seconds. So, in all technicality, if you're on the highway, you're aging slower than someone having a picnic watching you on the highway. I think I went way over. I'm sorry. That's all I had.
Thanks very much, and I guess we'll save questions for private discussion. Should we done this right at the start of the semester? or I think we should start the grad students.
Yeah. How do you get this?